We have reached stability in text-only language models. The current frontier is native multimodality, integrating disparate data types into a single system. These systems are called omnimodals. They are defined as a unified architecture capable of natively ingesting and generating multiple modalities within the same processing window. This creates an engineering conflict. Language is highly compressed, discrete, and symbolic. Physical image data is continuous, dense, and constitutes a passive observation of the world rather than an abstraction of it. Early attempts at omnimodals tried resolving this by forcing physical image data through the exact same tokenizer funnels used for text. This shattering creates catastrophic information loss. The resulting tokens lack the fidelity required for complex visual understanding tasks. The research suggests we cannot simply brute force continuous physical data into architectures optimized for discrete language. To maintain performance, these systems must bifurcate their training objectives to handle different data densities. They must also decouple their internal network parameters. Without this separation, the density of visual data tends to overwhelm the capacity needed for language processing. Transitioning to native multimodality requires moving away from unified parameter networks and towards specialized, modality-specific routing. The first attempt to unify these modalities, exemplified by models like Chameleon, was based on the hypothesis that we should discretize every input. This starts by slicing an incoming image into standardized 16 by 16 pixel patches. These patches pass through a continuous encoder, which converts raw pixel data into vector embeddings. These embeddings are then matched against a learned VQVA codebook. The system finds the closest discrete correspondence in the table, stripping away the nuances of the original continuous signal. The codebook assigns a specific integer index to each patch, effectively turning the image into a sequence of numbers. These image integers are interleaved directly into the sequence of text tokens. The model then applies standard cross-entropy loss to predict the next token in this mixed sequence, treating the image indices exactly like words. However, this creates a bottleneck. Discretization artifacts cause the model to lose the fine-grained information necessary for understanding complex visual scenes. There is also an efficiency cost. Generating even basic images requires a massive token budget, making the model computationally heavy compared to its output quality. Forcing continuous data into discrete indices creates an inherent ceiling for image fidelity, suggesting that a non-text training objective is required. The transfusion architecture addresses this by moving away from a unified cross-entropy objective. Transfusion maintains the interleaved sequence of text and images, but it processes the physical image data using a separate mathematical path. The image data remains as continuous patch embeddings. It bypasses the discrete codebook entirely, preserving the original density of the visual signal. The text tokens are routed to a standard autoregressive prediction head. This pathway uses a causal attention mechanism, which is designed to predict the next symbol in a sequence based on previous ones. Simultaneously, the image patches are subjected to a diffusion process within the same transformer. Instead of predicting the next integer index, the model learns to remove noise from the continuous visual embeddings to resolve a clear image. To capture full spatial context, the image path uses bidirectional attention, allowing the model to look at all patches of the image at once. While this dual objective approach solves the discretization problem, it introduces a conflict. Forcing both pathways through the same transformer weights creates competition for parameter capacity. The mixture of transformers, or MOT, was designed to resolve this capacity competition. MOT introduces modality-specific parameters directly inside the transformer block. Each modality gets its own set of projection matrices. A deterministic routing mechanism identifies the type of each incoming token. When a text token arrives, it is routed exclusively to the text parameters. The image weights remain dormant. An incoming image token bypasses the text weights and activates only the image parameters. After these separate projections, the data streams converge to perform the actual attention operation. Merging here is critical. It allows the model to maintain global context, ensuring the text can still influence the image generation and vice versa. The data diverges again as it enters the feed-forward network, which MOT also divides into modality-specific blocks. This decoupling results in lower validation loss for image generation and allows the model to follow fine-grained instructions more accurately without degrading its text performance. This separation also enables asynchronous training. An existing high-performance text model can be frozen, while newly added image or speech parameters are trained in isolation. By isolating data processing to specialized weights while maintaining a unified attention window, Moat solves the capacity competition problem. We have optimized the architecture through specialized routing and dual objectives, but these technical solutions have revealed a persistent paradox in multimodal training. To understand this, we have to map the relationship between a model's ability to generate data versus its ability to understand it. In text-only models, the relationship is a diagonal. Training a model to generate text inherently scales its logical understanding. This happens because language is a highly compressed abstraction of human thought. To predict the next word, a network is forced to learn the underlying reasoning and cognitive logic encoded in the tokens. But the visual trajectory is different. Even as generation capabilities scale up, there is no corresponding gain in physical understanding. This asymmetry persists regardless of the architecture. Even with Mott's optimized routing, we find that raw pixels remain a passive, redundant sensory signal. Unlike text tokens, pixels do not inherently contain a logical roadmap of human reasoning. Simply predicting the next frame, no matter how efficiently we route the weights, does not currently yield the same emergent spatial intelligence we see in language. The next major frontier in AI is not just about weight routing, but discovering representations that can compress passive sensory observation into the kind of logical abstraction we find in words.